Why are we bringing daylight into computer screens? Of course, it's a basic necessity for health, and we can all feel that, but there's also a growing body of mechanistic understanding as for why we cannot just simply replace sunlight with some electric light source. Starting with the most popular topic, blue light, which is really not where the focus should be, as we will soon see. But so part of the blue light question is indeed that short wavelength light is important for setting our internal clocks. And a good 25 years of research has clearly shown that ample exposure to blue light in the middle of the day is necessary for proper daytime activation, which in turn is also important for getting a good night of sleep subsequently. And displays are quite effective at delivering such circadian stimulation, so part of their potential harm comes from cueing daytime at night. But then there's another aspect to the potential dangers of blue light from displays as well, which is much more slowly but starting to get recognition, and that has to do with the fact that blue light is a physiological stressor. And that's true in the whole body, but it's particularly true in the retina, which is of course directly exposed to light, but it's also the place in the body with the highest metabolic demand. So oxidative stress has significance for eye health and also for visual functions and digital eye strain, which I will detail more in the next presentation. And so for a long time, display companies tried to ignore this issue, but nowadays they are increasingly embracing it with more or less suited products. But so how does this work? That there are these two aspects of blue light. One of them is desired and actually necessary for proper daytime activation, and that is linked more to the long wavelengths of the blue range, while the other aspect is always considered harmful and undesirable, and it's linked more to the short wavelengths of the blue range. So if this is true, and there is indeed some 40 nanometers difference between the two, then of course we should separate them to only get the good and never the bad. And this idea actually works to some degree. Eyewear companies produce filter products based on this rationale, but the idea kind of suffers from two major issues. One of them has to do with that these two different aspects of blue light differ in their peaks. However, the peaks belong to some bell-shaped sensitivity curves, which therefore overlap greatly. So in practice, the two effects are only separable to some small degree. And the other aspect, or the other problem with this rationale, has to do with the evolutionary picture that Liliana painted in the previous presentation. And this relates to that daylight triggers both effects together, and naturally they always come together, even if in slightly different ratios. So how does that work then? Do we all have to put up with age-related macular degeneration just to have a good circadian rhythm? Well, actually, this is asking the wrong question. The two aspects are inseparable in the spectrum because they also belong together in physiology. So both the circadian and the tissue damaging effects of blue light come from the fact that it is a stressor, which is necessary in the right place and at the right time. So on the systemic level, we all understand this to be true. That's why we exercise, even though exercise itself creates damage, but that's good as long as we can recover afterwards. And this logic also applies all the way down to the lowest cellular levels. So preventing the harmful effects of blue light hinges on our ability to recover from that photochemical harm. And this recovery has a temporal component. This is the one that circadian lighting has been recognizing for a while, and I think now most everybody have heard of it. And it has to do with stress in the daytime is good as long as there is ample recovery afterwards. And that's why we need dark nights and good sleep. But then the second aspect is a spectral one, and that is only lately starting to gain some recognition. And it has to do with that damaging effects from short wavelength light can occur quite quickly. And so it is also important to trigger those mechanisms which facilitate recovery concurrently to when the photochemical harm is happening. And so these the wavelengths which trigger these recovery promoting mechanisms are always present in daylight, and they belong more to the long end of the visible range, deep red and near infrared frequencies, while these frequencies are always missing from electric light sources, including from displays. So these healing frequencies at the long end act in the opposite way to blue light, and so in short, blue light creates oxidative stress, while deep red and near infrared frequencies help bring oxygen to where it is needed. And this recognition is behind the great success of photobiomodulation applications. So the most common kind of simplified view of how it works is the following. Mitochondria are the engines of the cell, creating ATP, which carries usable energy for all kinds of cell functions. And both aging as well as the effects of tissue stress happen through the same process, which starts with mitochondria deteriorating and producing less ATP, and therefore the byproducts of cell functioning begin to build up. And these create a toxic acidic environment which triggers an inflammation that further decreases mitochondrial functioning, and less ATP is available, and with that a vicious circle closes. And so as too little energy is available, these toxic deposits keep building up and eventually the cell dies. But this vicious circle can be broken by deep red and near infrared light through temporarily triggering increased ATP production. And once enough energy is available for the cell to clean up these toxic deposits, proper cell functioning is restored, and the cell survives. And indeed, a lot of research by now supports this model and shows that we can actually really trigger recovery and prevent cell death, including that from blue light, by using certain frequencies of long wavelength light. However, there is also evidence that generalizing this model to all near-infrared frequencies is probably incorrect, because all else being equal, some frequencies of near-infrared increase, while other frequencies of near-infrared decrease ATP production. So for therapeutic applications for promoting recovery and increasing ATP production, narrowband sources like LEDs and lasers are the most effective, because they can trigger these ATP increasing effects and not trigger the adjacent ATP decreasing effects belonging to these wavelengths, which are just maybe 50 nanometers lower or higher. However, in nature, these different effects always come together mixed, and they are mixed with different ratios depending on the angle of the sun and other factors, which then provides more nuanced regulation and dynamic changes with circadian and circannual and other cyclicities in the corresponding bodily functions that they trigger. So far I've been only talking about one dimension, and that is of mitochondrial metabolism, and the picture is already not so simple. But then if we zoom out a little bit, we find so much more, because mechanistically, mitochondria do more than just energy production. They are important to regulate all kinds of cell functions, but also light acts on other parts of our tissues, for example on cell membranes, and they modulate ion channel behavior. And so in clinical practice, correspondingly, we see that each part of the spectrum can be used for a different purpose. For example, again as before, near-infrared light can be used for tissue regeneration through increased ATP production, but other frequencies of near-infrared light can also be used to decrease ATP production and thereby to, for example, minimize reperfusion injury around a stroke. And red light, very importantly for us, can be used effectively for myopia prevention or for curbing age-related macular degeneration, but also for skin rejuvenation and recovery promotion in all kinds of body parts. But then yellow light can be used through likely a different mechanism for specific skin problems. And green light, yet again through different mechanisms, through M-cone mediated pathways, can be used to treat neurological problems, but also for bone repair, etc. Basically, each part of the spectrum has specific effects, and light affects physiology through many different mechanisms. And these are in a web of complex interactions, some of which are antagonistic. As we saw before, blue light and red light are antagonistic in certain ways, as well as some parts of near-infrared light to other frequencies of near-infrared light can also act in antagonistic manners. But some interactions are more complementary. So, for example, in photobiomodulation applications, red light in the mid 600 nanometers range is very frequently used together with near-infrared light in the mid 800 nanometers range. Because the two are slightly different, they likely act through somewhat different mechanisms, but they act in the same direction. So combining the two is more effective than using twice the intensity of just one or the other. And in daylight, these different effects never come in isolation. They always come mixed together with varying ratios, which provide dynamic cues for our physiology. And so the stressor effects of high energy, short wavelength blue light always come in natural light, counterbalanced by the recovery promoting effects of deep red and near infrared light. And this is true in daylight basically always throughout the day with different ratios, but it's kind of never true in electric light sources or in displays. And so this was just a brief list of the most important light physiology considerations behind our approach to PIXAN. In the next presentation, I'll be similarly going through some visual effects of modern computer screens, which are perhaps lesser known.